Yeah, no,
Okay, everybody can see the desktop?
yeah, right.
Okay, let's just start then. So today's topic that I will be presenting is on the white paper, which is architecting cloud applications for AWS, which includes the design principles and best practices. Now, you guys can ask the questions anytime by interrupting me, and this let's make it as an interactive session as much as possible. So, before we start, let's clear out some of the cloud myths. Um, um, because this session that when I read the white paper, it is actually an overarching umbrella session that actually covers all the topics that we have learned so far. It includes compute, it includes cloud, it includes architecture, design, includes security. So many things are included in this session. The white paper was quite dry, so I would try to make it as interactive and as interesting as possible. That is why instead of going through the white paper directly, I have made the points in the presentation so that we can have a meaningful session. First things first, let's clear out some misunderstandings on the cloud before we begin our design session. The first misunderstanding is that many people go to the cloud by saying that the cloud would bring cost savings as compared to whatever that they are hosting on their existing on-premise data center. That is not necessarily true. And if you see in 3 years run, the cloud cost is exactly the same or almost the same as the on-premise infrastructure. The way that cloud can bring in cost saving is the architecture that you design in the cloud is rightly sized rather than peak sized. Because when you design in an on-premise infrastructure, you design it based on your peak loads, while in the cloud you design it based on the actual load that is on your environment. For example, if you want to buy a firewall, you would buy a firewall seeing your 3 to 5 year return on investment and depreciation and the peak load that you can expect in those 3 to 5 years. But in the cloud, if you want to buy something or a server or a firewall or anything, you can just rightly size it and then grow as your requirements grow. So in that way, you can do some cost savings, but in not necessarily if you misunderstand this myth and design the cloud just like you do on the on-premise data center, like um, put a 10G firewall or something like that, similarly, or like huge servers that you basically provision on on-premise, then the cloud cost will not will actually be higher rather than lower. So this is what misunderstanding number one. Second misunderstanding is most people think that okay, we have hosted in the cloud. Cloud is reliable. It has availability of 5 nines, and it would never go down, and it is better than our data center. That is not necessarily true, and you guys have already seen like 2 months ago when Amazon's S3 went down. So this is not necessarily true. So the application should be designed in a way that it can sustain multiple cloud regional failures, and cloud gives you the ability to do that. The third myth is that cloud is similar to our traditional hosted services, which many of the data center services vendors provide, and you can just host your direct your servers there, and then you forget about them, and it would just be a monthly bill that you can pay. This is not entirely true. You can still host your servers there, but cloud is much more than that. It provides certain level of managed services, certain level of automation, certain level of security that is not available at all in the managed services environment, in a traditional hosted environment. One of the key point in point number three is that in a traditional hosting environment, you would know where your data center is and you can physically go and see that. While in the cloud, you would never know where your data center is. You would know the region, but even like in the case of AWS, nobody knows where the data center is in that region and where it is hosted. This is for security purposes so that physical attacks can be avoided against the data center. Even within AWS, only a certain member of the teams know the exact location of the data center because they have to do data center operations. The sales teams or the solution architects or other people don't even know where the exact location of the data center is. Point number four is cloud is easier to manage and you can reduce your staff because cloud provides automation. It provides so good things that you can like manage. it on your own. That is not entirely true. You have to have a staff that is actually expert in the cloud. You may have to replace your existing staff to a more suited skill set that provides the necessary skills for the cloud infrastructure and the applications and automation. But you not necessarily you have to reduce your staff. It is not easier to manage. It is exactly almost the same as the traditional data center, but in a different way, where you have to manage the cloud applications and cloud services and managed services rather than worrying about the underlying hardware. The fifth myth is that most people think that cloud is less secure than traditional data centers. It is also wrong. Cloud is equal or more secure, as Ali has already explained that many of the unique things in the last session. We saw that security is at top notch in the cloud. It has all the certifications, it has all the technology in place that actually makes it equal or more secure than a traditional data center. So this is just a introduction to the misunderstandings on the cloud. Um, Now we'll begin our architecture best practices. This is the white paper that we will be referencing to, which has been shared before. So we'll be discussing the architecting for the cloud AWS best practices. And the whole presentation is based around the cloud computing difference and the design principles points. And I have not added anything out of the white paper, although there can be many things added in terms of best practices, but I've primarily focused on the white paper because the session is actually focused on the white paper itself. So any questions till now before we proceed? All right, then we'll proceed further. All right, starting from the cloud computing difference, the number one, this heading, the cloud computing difference, defines what exactly is different in terms of the traditional environment or the legacy environment that we called on-premise data center or managed hosting environment. What exactly has changed in the cloud computing environment? So the point number one is IT assets has become programmable resources. What does this mean? This means that anything that is in the cloud is a programmable object. That object can be a server, it can be a database, it can be a storage, it can be any service that you can consume from the cloud, even your network interface card IP address, your security group, your storage, your EBS volume, your S3 volumes, all of these are objects in the cloud. They can be migrated to a different region, they can be migrated to a different availability zone, they can be deleted, they can be recreated, they can be backed up. And all of this can be done programmatically, and automation is included in that. Uh, Being a programmable resource, this means that the assets can dynamically scale to an indefinite number, and it can serve either one user or it can serve 1 billion user using the same architecture. And we will see going forward how it can be done. And the good thing about cloud is that since it's a programmable resource, you just have to pay what you use. You don't have to pay anything extra. So that is where the cost savings come into the picture. The second point that cloud computing difference makes is that you actually don't need to know how to program these resources. AWS makes it very easy for you to roll out new databases, roll out new servers, roll out new images, backup new images, do a multitude of managed services on the infrastructure with the single click of a button or using a console or using an API. So when we say that you don't need to program, that means that AWS takes that hurdle or that take that pain away from you so that you can focus on the actual applications. You don't have to worry about where the server needs to be, whether the server's warranty is expiring, whether the server needs to be um, replaced, or it's going end of life, or any sort of other stuff like that. Uh, Having said that, once you are able to focus on applications, you can deliver new solutions much faster than by if you compare it with the traditional infrastructure. And these solutions can be dynamically scaled to an n number of servers or n number of objects or n number of resources. That means that, say, for example, if you want to host an application in your on-premise data center, you have to take care of the internet bandwidth or firewall throughput or the rules or how much compute you have, how much storage you have. You don't have to worry about that in cloud. You can actually, if you want to host an application, you just host an application with n number of users, and then you just grow from there directly. So basically, cloud is designed for high availability and scalability from ground up. Now, when we say high availability, this means that cloud is prone to failures, but failures do occur in the cloud. So that is why the high availability needs to be multi-region, and the cloud can sustain force major events, which is like, any storm or any earthquake or such kind of events that occur, the natural disaster events that occur. You can prevent them by distributing your application globally. The third point is global availability and unlimited capacity. When you design your cloud, the cloud architecture is always rightly sized. That means you fix an n number of users, and you design the application or architecture according to those number of users. And then you make the use of unlimited capacity and global availability and expand your infrastructure accordingly to the cloud. And many different organizations have done that, just like Netflix, Dropbox, and other companies have expanded their infrastructure by starting very small and then exponentially replicating their infrastructure globally. You can optimize your application delivery to multitude of different regional networks, and Amazon or any other cloud provider provides the direct connectivity and other tools like content delivery, networking, and application firewalling across different regions, so that you can make use of these services and deliver your application to that region in an efficient manner. You can move your machines and data around the globe programmatically with the click of a button or with a script or something, which is actually not possible in an on-premise data center if you have. And in order to achieve the same on on-premise environment, there are quite a lot of investments required, and the infrastructure needs to be mature enough in order to do that. Business continuity for the applications is already built in. So once your application is globally available and distributed, it can never go down, regardless of wherever the data center has an issue. So the applications such as Facebook, such as Dropbox, such as Netflix, they never go down because they have business continuity and disaster recovery built into their architecture. So whenever a region fails or whenever a data center has an issue, automatically the content starts serving from other availability zone or other region. So when we talk about region, so you can actually expand your applications to multitude of different data centers, which is not possible in the on-premise environment, because you need to have that many data centers or hosted environments present across the world. But the cloud provides you with a single click of a button to move your applications from one data center to another data center, or just replicate the same setup to another region. The fourth point is built-in security, as I would not go in deeper into that because that has already been covered in detail. So AWS provides native security and built-in features that can provide encryption, that can provide compliance, they can provide data protection, which is actually quite difficult to achieve if you want to do that on an on-premise environment. Think of encrypting your whole data stores of VMware or your file servers or your physical data centers or SANs. It is quite hectic, but you can do that in the cloud by just using an IAM or encryption keys. Security policies are built into the programmable resources, so wherever your instances go, regardless of whether it's availability zone A, B, C, D, or any other region, security policies can stay consistent. And these security policies are on the instance level, which means that you, in order to provide the same level of service on on-premise data center, you need to have similar level of security on the virtualization layer in order to achieve the same result. And it has to be global across the across all of the data centers. So cloud makes it look very easy, but it is definitely a challenge to achieve in an on-premise environment. So moving forward, all of this can be combined into 6 main points, which is the AWS design philosophy. I would start with the picture on the right hand side, which says the first rule of distributed computing, which is everything fails all the time. This is the quote from Amazon CTO, which brings us to point number one, that we have to design for failure and then nothing fails for you. So, which means that if you keep failure evident in your design and your application and your infrastructure is designed in a way that it can cater for failures, then the application will actually be available. The second point that we'll be focusing on will be loose coupling sets you free, which means that your application cannot be in a single server. It cannot be a very tightly coupled application that cannot actually work with different components lying on different server. It has to be, in order to move to a cloud environment, the application needs to be loosely coupled. It has to have several different application components that can run on various different servers and that can talk to each other via the network communications. The third point is elasticity is key. That means that you have to make use of elasticity, and we will be talking in more detail in the next slide for that, which includes how vertical scaling is different than horizontal scaling and why cloud prefers horizontal scaling. Security has already been predefined that it has to be embedded in every layer. It has to be mandatory. There should not be a way out of security. Fifth point is think parallel. Parallel means parallel computing, horizontal scaling, not vertical scaling. And we will discuss in more detail in the next slide what is vertical scaling. The sixth point from the design philosophy is that leverage different sources of storage options so that you can make use of all sorts of storage to embed in your backup policies, in your storage policies, in your machine provisioning policies as well. So this ends for the first section of the presentation, which is the cloud computing difference from the paper. Any questions till now? Then we will focus on the second section of the paper. All right, we'll move to the second
Go ahead.
section.
Farhan, I have a small question. So,
Yes.
yeah. So let's suppose whenever the users are increasing by the time, and let's suppose we have to scale our any let's suppose we have to scale any external deployed firewall, and we have a limited firewall performance. So
Mm-hmm.
what are the ways available to increase the performance?
Yes. So, in order to increase the firewall, like say for example, you provisioned a firewall in the cloud that has a bandwidth of 200 Mbps, for example.
Hmm.
Uh, Now you have deployed this firewall, and the firewall is in place, and now it is getting over capacity. What you do is you deploy another firewall of similar capacity or higher capacity, because AWS believes in horizontal scaling, not vertical scaling. You don't have to upgrade that box to a higher number. You can deploy another firewall, and you can use Route 53 to do an active load balancing between the two sessions. And since the sessions are coming to a specific public IP addresses that are mapped only to the certain firewalls, then the return back sessions will also be going back through the same firewall.
Hmm.
So, I will explain this in my next slide how horizontal and vertical scaling works. And this is the way that should be done for regardless whether it's a firewall, whether it's EC2 instance, or it's an application group or a database server group. It needs to scale horizontally rather than vertically.
Okay. So could we
So
also
you can
get
deploy.
behind the load balancer by adding more instances behind the load balancer?
That is also one way to do, but the load balancer then has to be AWS defined load balancer that should not have limitation on the bandwidth itself. That is also possible.
Okay. Okay. Thanks.
Okay. So now we come to the second part of our presentation, which is called the design principles. If we go back to our presentation paper, you would see that there are several design principles, 10 to be exact, which are presented in the paper, and we will be going one by one through them. So first one is scalability, then disposable resources, automation, loose coupling, servers, databases. All of these will be covered in this slide. So starting from the first one, which is scalability. So when we design for cloud, the scalability can be done in two ways. First is you deploy a server and then you keep increasing the server size in terms of compute power. Like say you deploy a 2-core server with 4 GB RAM, and now you see that it is getting over utilized, then you increase the power to 4-core 8 GB, then you increase the power to 16-core 32 GB. This is called vertical scaling. You keep on increasing the server sizes. Now this is not the preferable way to do in AWS. AWS always believes that you start small and you keep on putting the same exact sizes uh, in terms of scaling together. If you see the horizontal scaling part, and you keep on uh, distributing the load across multiple smaller workloads. The benefit of this is like if a smaller workload goes down or it is crashed or if you destroy that, not a not a huge number of requests are impacted. Think of it in a way that you are a businessman and your one of your payloads is going on a truck on a highway. Uh, like you hide a big truck and put all of your payload in that truck, and you expect the truck to reach on time on the other side of the destination. Now, if something happens to this truck, maybe some accident, maybe a tire puncture, maybe or something, all of your payload will be delayed. Now, think of another strategy like you hire small pickups, like say maybe 50 or 10 or 100, and then you distribute your payload and then you send them from various different highways to the same destination. So this is completely distributed, and even if something happens to the highway, even if something happens due to a force majeure event, still some of the workloads would make it to the destination, and you would still some part of it will be successful in reaching the destination. This is what Amazon prefers, which is horizontal scaling. But in some specific applications, we cannot do horizontal scaling, like for example databases. So we do vertical scaling on that. Now, this is an example of horizontal scaling, how you do horizontal scaling. This is a typical architecture of a web application. So you have Route 53 here, you have the users here. The users enter into Amazon Elastic Cloud by Elastic Load Balancing application. They go to a CloudFront, and from CloudFront they go and download the images from S3, and then they go to various different servers. Now these servers can be M3, C4, M4, or any different type of application server that you want, but it has to be of same size, and they should have auto scaling at this layer. Then all of these servers actually talk to an application layer, which is again an auto scaling layer, and is behind the load balancer. And this application layer talks to a database master instance, which is a vertical scaling instance, and that is replicating to a secondary node instance. So this type of typical architecture is designed in AWS in order to serve either one user or 1 million users. Think of it like if one user is accessing, your auto scaling would kill all the servers and just keep on running maybe one server, and you would just pay 981 USD a month for running one server instance or minimum whatever instance that you want to run. And as soon as your workload increases, automatically the programmability from Elastic Load Balancer would trigger multiple instances that increase in size horizontally by adding more servers here. up to a threshold that can be a defined figure of say 100 instances or 1000 instances depending on the user load, and automatically it decreases as well as the load goes down. Now, as far as the content serving is concerned, which includes video files, image files, and any other things, these can be hosted in S3, and these can be cached in your CloudFront CDN. All of the servers that are the web servers that are hosting the content always refer to all the images and video files that are hosted in S3. And you might have already seen this in Cisco Live 365 slides. When you download your presentations, they actually come from S3 because because Cisco has hosted their Cisco Live 365 on Amazon itself. So whenever somebody is downloading a presentation or a file that is a huge content, the content goes directly from S3 and there is no load on the server. So basically you can reduce the server size and you can run them on a very minimal scale. Now, if we jump to the application layer can be defined in the same way, or it can be completely serverless as well. We'll discuss that in a little bit. Now, when we come to the database, currently there is the database technology is not that mature that can actually do that kind of scaling other than NoSQL databases. So if you're talking about structured databases, there has to be a single instance that needs to be vertically scalable. So here the vertical scaling would come into the picture, and you can scale the databases based on number of cores or memory and other stuff. So when you are designing for scalability, you need to see CDN, you need to work on Route 53, you need to work on a scalable load balancer. There are two types of load balancers available in Amazon. One is an application level load balancer, which is a layer 7 load balancer, and there is an elastic load balancer, which is a traditional IP level load balancer. You have to work on the front end component, which is the Elastic Compute Cloud on the first layer, which is your front end layer, which can host your web servers like Apache or IaaS. You can also publish an scalable API directly here if you are hosting a mobile application and that works on API. You need to host your DB in RDS with multiple AZ replication. And all of these need to be in multiple availability zones. I have shown here 2 availability zones in gray areas here, but you can host your application in as many availability zones as you want. Now, if you notice, S3 is not shown in any availability zone because it's availability zone independent, it's region specific. So you can use S3 as a completely region independent service. Any questions still here?
No.
Guys, either I'm very good at presenting or you guys are sleeping. There can only be 2 ways.
No, no, no.
Second way, I think.
Good man, good. Please
Question.
proceed.
Yeah, your one question. You are saying scalable DNS. What does scalable DNS mean? Using
Yes,
Route 53
scalable.
only.
When we talk about DNS, we talk about Route 53. So Route 53 is actually a service that can scale to n number of queries. You don't have to actually host a DNS server.
Yeah, scalable means only Route 53, not any other DNS server like.
No. So any other DNS service if you use, that will not be scalable because it will be hosted on a server within, like in the context of Amazon, it has to be hosted on a server because Amazon only provides Route 53. Now you can use any external DNS service also, which can be GoDaddy or Dyn or any other service that can actually still route to these services, but then the capabilities of Route 53, like failure detection of the instances or increasing using the auto scaling, will not be there. So you have to be very careful in choosing which DNS service you would want to use. I would always prefer that Route 53 should be used. I'm even using Route 53 to automatically and dynamically load balance the traffic between Etisalat and Do as well. So all of the websites that are hosted on premise as well in our environment are dynamically load balanced via Route 53.
Any idea? Is it Citrix GSLB or something
It's
else?
it's an open source implementation of Bind DNS, which is
Mhm.
actually intelligent enough to detect the service failures and other stuff. So it's not using any Citrix or F5 code, as far as I'm aware.
Oh, oh, okay.
But it has all the features of a GTM and GSLB type of features.
Yes, because ELB could be Citrix Vox probably.
Hmm.
Uh, ELB could be a Citrix Vox. If ELB is a Citrix Vox, Route 53 could be a Citrix GSLB.
Hmm.
But anyways, okay, great, great.
Okay, so this brings us to our second point, which is loose coupling. So again, we will refer to the same architecture. So when we talk about loose coupling, we talk about stateful and stateless components. Now, what is a stateful and a stateless component? A stateful component is a component which has some level of relationship with the user. Like when a content is being served, the user will have a sticky session or a cookie or anything that can actually provide some level of information about the user so that the web server can serve the content. So these are all called stateful components, and when the user is getting the content served, this content will be pushed by the load balancers. It will be extracted from the web server and pushed to the user by the load balancer. And load balancer maintains all the sticky sessions. This is like a typical implementation of our web server, in which you deploy a number of web servers or application servers, and they use sticky sessions, and these sticky sessions either based on source destination IP addresses, different cookies, or any other way of identification in order to stick the session to a specific server. The problem with the stateful session is that if that instance has a problem, and if it is goes down, then the user that is getting the content from that specific server will be impacted. And this is quite typical and quite difficult to avoid in case of stateful applications, if the sticky sessions are maintained by the load balancer, because the load balancer will be sending that specific sticky session to a specific server, and if that server goes down, certain number of users that are on that server will definitely be impacted. Now, how does what is the solution to that? The solution to that is stateless components as a service. What is a stateless component? Stateless component has a backend API, which can be a queuing service, such as Amazon Simple Queue service, or it can be um, uh, an Elastic Cache, which can be an in-memory caching server that can actually take the sticky sessions out of the load balancer and from the server and host it elsewhere on a different environment. And we'll discuss that in slide number 21, how it works. But that can actually make the application completely stateless. So the state of the user, what exactly the content is being served, is extracted from the load balancer and the server and is hosted in a different environment, in an Elastic Cache or an Amazon Simple Queue service, and this can actually make the applications completely stateless and independent of server failure. So even if a server fails and the same request is served by another, has to be served by another server, that server can go to that central cache and get the user's details of what exactly the user was doing, whether he was filling the form, or where exactly he was in the registration or the process, and it can actually, the user can continue from there. So that is where this makes a lot of difference when you are doing a transactional based application. Say, for example, in an airline, you are booking a ticket, and in between a server goes down. What will happen exactly if it's a stateful application? Stateful application will give you an error on the next. As soon as you click the next, you will get an error and you will get frustrated and you would choose another airline. Now, how would airline overcome this issue? They deploy stateless component. What they do is they save the state on every state, on a separate server, which can be Elastic Cache or a simple queue service. And as soon as you click next, the request is gone to the load balancer, and the load balancer actually looks for the session or the cookies in this Elastic Cache, and then serves the right content from any server. So this is how the stateless components are implemented. This is actually more of a solution to a problem that was very much there for a very long time. All right, so we are done with point number 2. Any questions with loose coupling?
Can this RabbitMQ or AMQP be used
Absolutely,
within application?
absolutely.
Yes.
Yes, yes. Elastic Cache is actually an implementation of a cache called Redis Cache, which is
Mm.
actually an open source implementation of RabbitMQ.
Yeah, because that will be easier to implement between the applications, right?
Yes, yes. So
Either if
if
you're doing automation
yes, so
or
if you want to do RabbitMQ, better to check. I'll show it to you in slide number 21. This is the cache cluster. The Elastic Cache is actually based on RabbitMQ. So you can use that, and actually it's a AWS implementation of RabbitMQ.
okay, great, great.
Okay, so that brings us to our third point, which is automation. Now, automation is a very wide word, and very different levels of automations have been achieved in on-premise infrastructure, in IaaS based servers, and in cloud. So when we talk about specific to AWS environment, we talk about mainly 6 points which are mentioned here. When we talk about automation, we talk about something that you configure or you schedule, or uh, there is an event against which there is an action that needs to be triggered. This is what automation does. So when we talk about automation, the first point is serverless architectures, and we are going to discuss in detail about the serverless architectures when we come to serverless architecture point, which is no servers anymore. So what serverless architectures does is that it lets the developers upload their code, and that code is executed in the environment without any server. So Amazon actually does this using the Docker container. So whenever you upload your code, it goes into a Docker container, and that Docker container actually runs the code. Now, if one user is accessing, that same Docker container can serve that code. If 10 users are accessing, if the same Docker container has the capacity, it would serve. But as soon as the utilization of that Docker container goes above 70%, automatically another Docker container is instantiated, and automatically the same code is uploaded there. And this is all transparent from our eyes. It automatically happens at the back end. So basically, you just upload your code, and Amazon rightly sizes your architecture. If 0 users are accessing, there will be 0 servers running in the code. This is like a breakthrough architecture in which you have to pay zero money if 0 users are accessing. Think of it like all the non 9 to 5 organizations that keep their application servers running all the time. Uh, think of it like how much they can benefit from this. Like they can actually keep their architecture running based on the user request. So as soon as 9 o'clock, users come in, a lot of users comes in, automatically the Docker container farm is instantiated, and it is sized according to the user request. 1 o'clock, users go on lunch. The Docker container is reduced to 10% of its capacity because that many users are accessing. 5 o'clock, and the last user goes from the office, automatically the Docker container goes 0, and don't have to pay anything for that architecture. But the main challenge around serverless architecture is your application needs to be designed very carefully in order to sustain in serverless architectures. Take applications like Microsoft SharePoint, like Exchange Server, all that cannot run on serverless architectures. It has to be a web application, Java code, PHP code, R code, anything that has to do with open architectures can easily run in serverless architectures. When you talk about EC2 auto recovery, if you by the time now by the time like CloudWatch can monitor the whole cloud architecture. So when we talk about CloudWatch can report a certain instance that is underperforming and has high CPU utilization, and because of some error or high memory utilization because some garbage collection was not done properly, it can automatically recover that EC2 instance with a specific event trigger, and you don't have to worry about that, and you just get a message that automatically the instance was cloned, and the traffic was shifted to the new instance without any downtime. So this is again a form of automation. Auto scaling, we have already discussed that you can maintain a certain level of application availability and scalability under predefined thresholds, similar to
Sorry,
what serverless architectures does.
sorry, one question. This EC2 auto recovery can we compare this feature with VMware HA or FT kind of feature?
Yes, yes, more or
Yep.
less. It's the same feature, but
Internally.
I'm not sure how in VMware we do FT. Do we have a some certain level of monitoring service that actually is monitoring the virtual machines?
Yes.
Okay, then it is the
Yes,
same
I think.
level of feature.
Okay. And serverless architecture is Beanstalk, right?
Yes.
So,
It's
how?
not entirely Beanstalk. I just mentioned Beanstalk as an example here. It can
Hmm,
be Lambda also. It
hmm.
can be Beanstalk also. Anything that has got nothing to do with servers and has got to do with the code is a serverless architecture.
But then it will be having some dependencies on the LAMP kind of code, not like
Yes.
Microsoft application. We can't run
Absolutely.
those
Microsoft
inside
applications
Docker.
or closed source application. That is why it says upload the code. So you cannot upload an executable file. You have to upload a code there in order,
Yeah.
and on top of that, Amazon actually optimizes that code also. So I have personally seen that if you execute that code, it on your on-premise environment, it takes, say, for example, 10 seconds to display the web page with a certain content. Amazon
Hmm.
optimizes that and is able to display in 7 seconds because they do a lot of optimization, compression, white space deletion, lots of other stuff that actually can be done in Java or PHP code. They automatically do that. They compile it with the best compilers, and the code
Hmm.
runs quite efficiently there.
So they have to parse the code first, then compile it, and then run it, right?
Yep.
So parsing, like removing all the redundant information and then like
Yes.
memory optimization and all those things.
Yes.
So,
Yes.
okay, great. So on Docker, how it will scale automatically or with ELB?
No, it does it automatically. Actually, serverless architecture, you don't have any visibility. ELB is automatically created, Docker Farm is automatically created, everything is automatically created. All you have to do is just upload your code and just let it run
Yeah, so it will be same like having ELB and VM rather than just upload the code and it will deploy the infrastructure for your code
automatically. Yes,
automatically.
yes.
Yes. So
And
the
it will
behind the
destroy
scene,
the good thing is it will destroy the infrastructure automatically as well.
so it is using in fact, it is using the same thing like ELB. If there is no request, it will destroy the EC2s, and then later on it
It
will.
will discard the EC2s, but it will still keep on certain number of EC2s running. It cannot destroy all of them. So you will
Yeah.
always have to pay a certain fixed amount towards your environment. But in serverless architecture, it completely destroys everything.
Yeah, so it kind of Docker running inside a VM, like multiple Docker instance
And
inside one virtual
I
machine.
have personally seen, you know, how much time it takes to initiate a code and a Docker. It takes 12 milliseconds. So 12 milliseconds,
Yeah.
the first
Hmm.
request comes,
Hmm.
it creates the whole architecture, runs the Docker, uploads the code. Within 12 milliseconds, your first request is served.
Yeah.
It is that
Yeah.
fast.
Yes. Revolutionary. Great,
Yeah.
great. Thank you. Thanks.
So now moving towards the CloudWatch alarms and events. So there is a service, monitoring service in Amazon, which is called CloudWatch. You can use this to perform two main items, which is one is alarms and another one is events. There is a major difference between the two. First is like you can send alarms to your network operations or your cloud operations team, so that, like, you know, they can have an environment notifications that okay, some instances are going down, up, or high utilization and other stuff. Or as a part of automation, you can trigger certain actions based on certain events. Say, for example, my some of my instances, if the CPU goes above 70%, they should be doing something. They should either be triggering a new instance or cloning a new instance or upgrading the size of the instance to a different capacity, or they have to do some action against it. Now this action is done by a component in Amazon called Amazon Lambda. Now, Lambda is again a serverless architecture that can actually do a lot of stuff uh, on your behalf. For example, why I use Lambda? I have a syslog server in Amazon, and say from all of my shopping malls, the logs are going there. Now I need to perform a certain action in these logs in order to normalize them, in order to add timestamps to them, or in order to add locations to them. This is triggered by Lambda. So the log goes to a Lambda function through the Kinesis Firos alarm, and from there it automatically adds the required information and then sends it to syslog. And this happens only when the log comes in. When the logs are not coming, the Lambda function is sleeping and it doesn't consume any of the infrastructure. So Lambda is like a cron job in Linux. It can schedule an event. It can trigger automatically as a part of a CloudWatch alarm, or it can do independently on their stuff. Now, Amazon has extended the Lambda function this year, and they have introduced something called green grass. What is green grass? Green grass is a very lightweight Lambda that can be deployed on any of the IoT device like Raspberry Pi or any of your Arduino boxes or any other stuff. And this green grass can be controlled directly from cloud. Directly from cloud. That means if you send a function like open my garage door or move that robot's arm, you will be sending that command to the cloud, and the cloud will send that command to your IoT device through the Lambda function. So this is again another breakthrough that Amazon has done. Coming to the second point of AWS lifecycle events, you guys have heard of Chef implementation. So OpsWorks is Amazon's Chef implementation with which you can do a lot of bulk configurations on your instances. You can perform yum updates. You can perform automated deployments. So this is all part of an automation in which you can use lifecycle events using the OpsWorks environment. Say, for example, I want to roll out a certain patch of Linux to all of my 1,000 instances. How would I do that? I would just use a chef recipe that does that. This is not a recopy, it's a recipe. Forward. So any questions on automation?
Any idea why Amazon uses Chef rather like Cisco going towards Puppet? So school of Chef is Amazon. Which one is Azure? Any idea?
No idea about that. I'm not very well versed in Azure because I personally don't like it.
But like Cisco, Cisco goes with Puppet, right? They are more
Yeah.
into Puppet. No Chef.
Cisco
Amazon goes
has
with Chef.
chef recipes also, but
Yeah.
Cisco, I'm not sure why Cisco has chosen Puppet. Maybe because Puppet has more libraries for network devices.
Hmm.
But what I'm seeing is that Cisco is moving more towards the Epic EM in order to do
Hmm.
all of these tasks repeatedly. But
Hmm.
Chef is the king in the Linux world. I mean, I'm not sure about Windows, but Linux Chef rules all the way. And there is another third contender, which is Ansible, which is very
Answer.
much popular in Linux, Windows, and especially Arista network devices.
Hmm.
And the main disadvantage for Ansible is that it's agent-based, which I don't like because you have to install
Hmm.
an agent everywhere in order to control all the instances. Uh,
Hmm.
for for Chef, it's from Amazon. It's very simple. You don't have to install any agent because you already have the metadata and API access for the EC2 instance. You don't have
Hmm.
to deploy any chef agent. You can just roll out your recipes directly.
Hmm. Great.
All right,
If
moving to
just one, sorry. If any of the automation or orchestration things fail, like in spinning up
Yes,
EC2 or something like that
yes.
automatically,
Always you
it,
can roll out a CloudWatch alarm.
CloudWatch alarm,
And
like,
that CloudWatch alarm can again be another event that can actually your backup that can actually be your backup plan. So you don't
yeah,
have to
it,
be like available. It can like maybe backup plan can be to route the traffic to some other region or some other availability zone or do
yeah,
whatever action that can also be done.
yeah, or static patch from S3 that okay, server not available kind of thing.
Yes.
Yep, yep. Okay, great. Thanks.
I think Farhan, Ansible is agent less, right?
It's agent based, right? Because we have to when I was working with the Arista, we had to install agents on Arista switches in order to make it work.
So the switches were not on like a SSH or something, or it was a proprietary some
No,
protocol.
it was on SSH, but in order to get the configurations and roll out the bulk updates and other stuff, had to install the Ansible agent on them. Ansible
Okay.
can work with SSH also definitely, but I think in order to get more, it's more of like a metrics monitoring and configuration tool. While Chef is like primarily update rollout and configuration management tool.
Okay, right.
So definitely Ansible adds the metrics section there. Like I mean, you can get much more data back from the agent, but then agent has to be deployed everywhere, right? That is actually a bit of a problem.
Okay.
All right, moving to the databases. This is a bit of a big section. I have two slides on that. So when we talk about databases, there are multiple types of databases in Amazon. Typically three types. One is the relational database, which is the structured database, which mainly includes the RDS service. Amazon offers multiple different types of databases. Now the world is more moving towards the open source databases. So when you design your AWS architecture, always prefer an open source database rather than Oracle or MS SQL. But of course, Amazon provides the instances for Oracle and MS SQL as well. Recently, Oracle has doubled their licensing price for all the cloud providers except their own in order to lure more customers back to them. But that strategy has actually backfired, and people have started moving to open source databases more than previously they were moving. So, my personal preference from a design perspective, and this paper also recommends that always use MySQL, Aurora, or any other deployment. But from an architecture perspective, scalability needs to be vertically as well as horizontally. You need to see whether the architecture of the database, like say for example, if you are deploying a Cassandra database, Cassandra is a distributed database. You can deploy it horizontally and doesn't break a sweat, which basically is DynamoDB. But if you're deploying a MySQL or MS SQL or Oracle cluster, that requires a physical node, a node that has a compute power, that has a memory, that has some allocated compute capacity allocated to that. That is why you have to vertically scale it accordingly. Now, from high availability perspective, always go for a multi-easy deployment because that would save you a lots of headache in terms of availability zone failures or any issues with the specific database. You can always have read replicas. You can have automatic failures to the standby without any manual administrative intervention. And when you shift from automatic by using automatic failure, the shift is almost instant. You typically don't lose any of the existing connections, provided that your application is designed in such a way. Applications, make sure that your applications that are connected to the databases are always using the DNS names rather than the IP addresses. Because if you tie down the applications with an IP address, most probably Amazon changes the IP addresses every week, so your database will go down. So relational databases. Amazon Aurora, Amazon MySQL, MariaDB implementation, Cassandra implementation. All of these are the databases that are relational databases. You guys can use that. There is another service from Amazon called DMS, which is the database migration service. You can connect DMS to your on-premise, any on-premise databases like Oracle or SQL Server, and it can act as an interpreter and move the data in real time from an Oracle database to open source database like Aurora DB. This is the relational database part. Moving to the NoSQL databases. So what is the difference
Sorry.
between a relational?
So, so it will migrate from Oracle to Aurora, but it won't migrate it back, right?
No,
So it will
no
be just one
migration.
way,
It's a migration service, one way.
one-way service for everything. There isn't any service which migrated back from open source to Oracle or SQL.
There is no service. Even the service, the DMS service was not there. Amazon has created this service on the customer's request in order to move away from Oracle.
Okay.
So DMS is one way path. If you want to move from Oracle to anything that is in the cloud and open source, you can use that. But if you want an Oracle instance in the cloud and you want to synchronize your data, then most probably you need to buy a Golden Gate license, and then you have to synchronize your database objects and schemas and other stuff from on-premise to the cloud environment. Active Data Guard would not work that well because of its nature, lock shipping and latency nature. So I believe Golden Gate is the best approach there, that side.
And
But
is
again, speaking to that, Golden Gate license doesn't come cheap. It's very expensive. So most probably people might not take that path as well.
so any tool from Oracle to migrate from open source to Oracle? No.
That I'm not aware of because
Got it.
not many people are making that choice, right?
Yeah, it depends. Like
And
depends.
there can be certain use cases where people might be moving from open source database to Oracle, but I'm not aware of any tools. Maybe someone else can provide any of their feedback in that sense.
Yep, great.
Okay, moving to the NoSQL databases. The difference between a relational database and a NoSQL database is that the relational database has a structure to it. It has a golden record. It has a tabular form. It has rows. It has columns. While the NoSQL databases are completely structureless. You can put the data in any way you like, and it just takes the data and keeps it somewhere and indexes it. The very nature of NoSQL databases have made them very fast and very efficient and uh, very scalable. Because since they can keep the data anywhere, that means that they are fully distributed. They can run anywhere, any place, and in any environment. The product from Amazon is called DynamoDB, which is the NoSQL database. It is a typical implementation of Cassandra. Cassandra, to be honest, is the NoSQL king of distributed databases. It can scale up to thousands, millions, trillions of nodes, and it can take the data in any way. To put things into perspective, Cassandra is being used by iTunes and iCloud, and they are running it on 18,000 node cluster. So imagine running Oracle on 18,000 nodes. It's simply not possible. Oracle cannot even proceed more than 2 nodes because the rack doesn't allow that. But DynamoDB is similar to that. It can scale up to thousands of nodes. It can, since it does this indexing in the memory, it is very fast and it is very scalable. Now, what is the use case of DynamoDB? DynamoDB can be used to place all of your unstructured data, which can be a real-time stream as shown in the diagram. It can be your logs from various different devices, which doesn't have any structure to it. And then once you store this data, you can you can do certain level of actions on them. You can do cleansing on the data. You can delete the records that you don't want, and then you can do various different complex joins, database operations on them, and then you can move this data to a structured database. So basically, it is like a big dump of your unstructured data, which is just lying there to be processed and fed into a structured database.
Like
The
it
benefit,
could be like user clicks, like click on specific URLs, right?
yes, yes. So a typical use case that we are using DynamoDB is the the location analytics. We are using DynamoDB to store the users databases there. We are using DynamoDB to ingest the syslogs that we get from all the environments. This is typically an architecture that we are using. So if you see, like, there are a lot of devices that are generating lots of logs, like a real-time log. It is fed
Mm-hmm.
into an Amazon Kinesis fire hose. Amazon Kinesis is again a form of serverless architecture, which is actually you can run any sort of server there, like, maybe you want to host, say, for example, syslog. Now, syslog runs on 514 UDP port, and you need a server to run for it. Amazon Kinesis exactly does that, but it doesn't know what this data is, what it has to do with that data. So it just acts as a very fast stream that can actually take the data, and then it can send it to the application servers or to the Lambda servers or to S3 bucket directly to store that data at the speed that the S3 or the servers can accept. Like, say, for example, you are getting the data on 1000 MB per second, but your server is only able to take 100 MB per second. Amazon Kinesis will act as a buffer in between, hold all the data, and then send the data to the servers on their own speed. From there, you can do some processing on the data. Like in our case, we are doing some processing. We are adding some attributes like location attributes or timestamps or any other thing through the Lambda function, and then we are putting this data back into Amazon DynamoDB. From there, it can perform many other stuff. So this is a typical architecture of a very fast real-time data stream application in which you don't want to lose any single event. Now, why we cannot use a relational database here?
Mm-hmm.
Because of the speed. Relational database, since they put everything in structure, very proper way, very efficient way. The thing is that very nature of structure makes them a little bit slow. So you
Is
could
it
end up losing real-time data stream. I'm not saying
is
it
it
cannot be used, but it can be
Mhm.
used, but it will not be at the speed of NoSQL database.
if I'm supposed to deploy ELK stack for logs, Elasticsearch,
Yes,
Logstash, Kibana stack, so I
yes.
can use the same kind of structure to keep all three of them separate and then stream
Well,
the data via.
ELK, to be honest, is a different architecture. ELK already has three components to it. ELK
Yes.
has the log stash as a
Mm,
Kinesis environment
mm,
in which you run your log server. You have an input stream, you have an output stream, and you are listening to the data on log stash. Then Elastic is
mm,
the database, which is like a flat file database. It is not
mm,
DynamoDB. It's not related to NoSQL or neither related to relational database. It's a flat
mm.
file database which keeps everything in flat files, and when you request, it goes and searches in the flat files using the index and comes back. And then Kibana is the front end which actually gives you all the nice graphs that you want. So in a sense, when you want to deploy ELK would not be, I would not say it's a NoSQL database, but it is a database that is based on flat files. So if you want fast speed or very high throughput from an architecture like ELK, you need to shift from Elastic to NoSQL.
But if like I'm not using DynamoDB, I can use Amazon Kinesis to stream all the traffic to ELK, right?
Yes, so you can still do that, but ELK will you will get Amazon Kinesis in front of Logstash, and
Yes.
then you will send this to Logstash. You can still do that.
Yes. Yes. Yeah. Okay. Great. Great.
Okay, the
Please
third type
proceed.
of
Yes.
database. Hmm? So third type of database is the data warehouse, which is the specialized type of relational database that is very much optimized for analysis and reporting and aggregation type of data. So it is, you can say that it is a modified form of RDS, which is capable of scaling up and scaling down dynamically. Now, the problem with RDS is, say you have provisioned a MS SQL server, okay, master server, and you have allocated 4 cores and 32 GB of RAM. Now, the problem you have faced is that this database is reaching its capacity, compute capacity, and you want to upgrade it. What is the way to upgrade? You have to take a downtime, uh, upgrade the node to a different version like 8 core or something, and then power it up again, like a typical EC2 instance, that how you would upgrade that instance. Now, what does Redshift do? Redshift brings scalability, the horizontal scaling to the RDS service. So what Redshift does is it automatically scales up, scales down based on the master-slave architecture, and it is SQL based, but it does massive parallel processing and stores the data in column form. That is why it's called columnar data storage rather than row forms. Normally, all the databases store the data in rows. It stores the data in column. Now, I'm not sure, but somehow columns are easier to process by processors. It increases the speed. I have not found any theory around that, but this is what the columnar storage says. Now, the good thing about the data warehouse in Amazon is called Redshift, and this Redshift is massively parallel processing architecture. It can increase up to 1,000 nodes or 2,000 nodes, and it can act as a highly capable compute cluster based structured database, and it can also be backed up to S3 as well. So basically, Redshift is Amazon's try to bring in NoSQL features into a SQL database, but it comes with a cost. Redshift is not cheap; it's very expensive. So here in this architecture, you would see that I'm using Redshift as a connection to my standard databases and using it for aggregation and reporting purposes. All right. So this finishes our database section. If there are any questions, otherwise we can move it to the fifth part.
No question, but there's just a mark because probably the columnar searches and data warehouse uses columnar is because typically in warehouse they use the similar type of data to so it doesn't do the horizontal row-wise searching. So it makes the search faster for similar type of data.
Hmm. Yeah, I think that defines the logic. Yes, agree. Okay. So let's move to the fifth point, which is disposable resources from the white paper. What does disposable resources mean? Now, most of the guys here might already understood that auto scaling allows the instances to be created, and then you can dispose of these instances in seconds as well. So RDS also scales to many nodes, provided that you are using service like Redshift, and then can be deleted as well. Everything else probably is a service which you use, you consume, and you dispose of, like Elastic Load Balancer, like CDN, like Route 53. So whenever you use them, you pay for them, and then you dispose of. So not many points here. The main point that the paper was trying to make is that you can dispose of resources whenever you want. Another
Does
design
anyone
principle.
know if
Yep.
can you hear me? Hello?
Yep.
Hello? Does anyone know if the Microsoft has those features as well?
Which features?
Like disposable resources?
Yes, pretty much every cloud provider has disposable resources type of feature in which you can provision the instances and you can dispose of the instances when you don't require them. So Azure definitely has this feature in which you can create the load balancers, you can create the CDNs, you can create the instances, and then you can dispose of as well.
Thanks.
All right, the next point is removing single point of failures. When we say single point of failures, we mean that any component in the whole architecture should not be a dependency for failure. So it should have the load distributed and the parallel architecture should be considered for those. So when you design your cloud architecture, it needs to be distributed to multiple availability zones. It needs to be engineered in a way that it can sustain availability zone failures, and the application should not be isolated if an availability zone failure occurs. Say, for example, if availability zone A fails, automatically the traffic should be routed to availability zone B using Route 53. So even using Route 53, you can route the traffic to other regions and you don't have to sustain any failures. CloudFront should be caching your content. So even if S3 goes down for a minute, you should still have your static resources cached in CDN, and it should not have a major impact till you route your traffic to a different region. So when we talk about single point of failures, it needs to be on the region level, it needs to be on the availability zone level, it needs to be on the load balancer and instance level. On all the service levels, it needs to be considered uh, uh, till the databases. So this is a very key point that you have to remove all the points that can actually hamper the service. Now, as a design principle, Amazon states that always make use of services, not servers. Say, for example, if you want to deploy a database, always makes use of RDS service rather than deploying a database on an EC2 instance. Of course, you can do deployment on a server as well, uh, but Amazon, from a design principle perspective, doesn't prefer that. For example, we were just discussing a couple of slides back about RabbitMQ and Simple Queue service, the difference between the two. So what Amazon recommends here is that you should make use of Simple Queue service, which is a similar service from Amazon. Rather than deploying a RabbitMQ server on an EC2 instance, you should make use of Simple Queue services. For content delivery, we always make use of CloudFront. For load balancer, rather than deploying F5 or Citrix or dedicated load balancer like Nginx or HA proxy, always make use of the services that are provided by Amazon because these are failure resistant. Their capacity is unlimited and they make use of the underlying architecture in a much optimized way. The elastic load balancers are completely elastic. They just expand their capacity as the load increases. So wherever it's possible, always try to make use of the services that are available there. A couple of while back, I raised a concern with Amazon that the NAT instances um, were supposed to be made as EC2 physical servers, like EC2 instances. And if those NAT instances go down, the outbound connectivity to the region it would be impacted. As a result, and this was not only my request, it was requested by many of the engineers across the board. They have created a NAT instance service, which is called a NAT gateway. And now this service is available to be consumed by anyone, and you can deploy these NAT gateways directly without using the EC2 services. So these NAT gateways are availability zone and region specific, and they can scale up and down as the load increases or decreases. Again, for deploying the databases like NoSQL databases, instead of deploying your physical, like your own databases on EC2 servers, Amazon recommends use the DynamoDB and EMR service. For search engine services, they recommend Cloud Search, similar to that, simple email services, S3, EBS, containers, and Beanstalk. So the main idea here is that always, whenever there is possibility, always as a design principle, use the services, not the servers. Now, extending this to the next level, what Amazon's paper is recommending is that you should use services 100% and go for all serverless architecture where possible, and do not make use of EC2 servers when it's not required. So in the architecture, you can see that there is an example mobile voting application in which the mobile API is published via the Amazon's API gateway. The votes are considered whenever a user votes, it goes to an API gateway. From there, it is routed to a Lambda function. From the Lambda function, the write gets executed into a DynamoDB, and the votes are the HTML page for that mobile application is served from S3 bucket, and the high availability is maintained by the Route 53 function. This is a typical example of a completely serverless application in which Lambda and API gateway and the S3 are being used to perform compute, request routing, load balancing, and content storage functions. So many more applications can use serverless architectures, provided that they are designed in such a way. So it is not only about infrastructure designing; it's about how the application communicates with each other and how the functions can how it can make use of certain functions and store the data. So in this typical example, all of the services of Amazon's were used, and none of the servers or EC2 instances were actually triggered. So this service actually costs zero when there is no voting request coming. Whenever the voting request comes up, automatically the infrastructure, the serverless architecture takes care of that. So this finishes our seventh design principle. If there is any question, then we can move to the eighth one. All right. So the eighth design principle is always make use of caching services that Amazon provides. Now, where could these caching services make a difference? Since most of the people are here from the networking background, so I would start from CloudFront. So CloudFront can be used as an edge caching engine, which actually can cache static content and some level of dynamic content as well. While caching, it can do various different functions, like it can do code optimization, it can do image optimization, it can do image optimization as per the device type. Like say, for example, if you're on a mobile device, you would get a different type of an image. If you are on a desktop or a tablet, you would get a different type of an image. And it can be a different, a whole lot of a different architecture for various different devices. And it can cache that content from the server. That can reduce the load on the server, thus reducing your cost on the server as well. So typically, I have seen that when you deploy CloudFront or Cloudflare or Akamai or these type of services, it reduces the server utilization more than 50%. That means if you were using an 8-core 32 GB web front-end server, you can reduce it and cut it in half, like 4-core or 16 GB, which is huge. Like, I mean, you would be saving about $300 a month for one server. And if you're running about 8 servers or 9 servers or 10 servers, you would save about $3,000 per month on just on the by activating the caching. Another benefit of caching is that it is distributed on the regional level or the global level, and wherever your users are, the closest destination, the closest caching site will serve the content, and that reduces the latency and improves the customer experience, and thus it gives an image that your application is performing very fast. Now, more towards the application side, there is another caching technology called Elasticache, which is an in-memory caching service, which is actually a database that is database of objects or key value store key and value store database that can be stored in a memory itself and which is accessible at a very low latency pace. This is very useful for applications which require referencing certain amount of data which can be useful for them, such as cookies, such as various different relationship between user and the servers. So this caching cluster can actually make server sticky sections completely go away and can store all sorts of your customer interaction information directly into the caching cluster, and it is accessible at very low latency, like sub millisecond latency, because it is hosted in memory directly. So this finishes our 8th point from the design principle perspective, that we have to use various different services from caching perspective, which includes Elasticache and CloudFront. Any questions?
Farhan, for this Elasticache, or you earlier mentioned Redis as well.
Yeah.
What is the like typical use case for this? I mean, this is not. I think it says cluster, but is it like the memory uh, cache is also shared among the different nodes?
Yes. So what it does is, like, there is a master-slave cluster relationship. So when you create an Elasticache, it's a virtual cluster that is created there, and each group actually serves certain number of objects. So the objects are served in various different cluster groups, and it replicates to a different cluster. So like, say, what I would say is, like, if one single node or a part of cluster goes down, the the objects or the key value store are not impacted, so it remains intact. So this was a concept that was brought up by some of the engineers at Facebook, which has been converted into different technologies across the world using open source. So the typical example of it is, as I've mentioned, like, you can store various different interactions from the user to the web server, which was previously being done by cookies and by sticky sessions. You can move those to an Elasticache, but in order to do that, your application needs to be capable of doing this. So what happens is that when a connection lands on a web server, the web server, instead of putting the cookie value in its own memory, it uses Elasticache and puts the memory there. Now, puts the information there, the key value store. Now, and if that server goes down, that information doesn't go down with the server. It is available there in the central cache cluster, and any other server can go and pick up that information from there, and the user can maintain its session, regardless which server is serving that. So by using this architecture, you can completely remove sticky sessions from the load balancer, and the application can be completely stateless.
Excellent. And this is because this has a very high latency requirement. So this
Very
is
low latency requirement, yeah.
yeah, very low. So is it per availability zone? Is it like restricted?
Yes, it's only restricted to availability zone. It cannot be cross availability zone. I mean, it is restricted to a region, not availability zone. It can sync with the different servers in different availability zone, but from same availability zone, the request will be served by the same replication group. So the request always travels within the same availability zone. It never goes out of the availability zone, because the latency would increase then. So say, for example, in this environment, I have the API servers in availability zone A and availability zone B. So when the request is sent by these two M4 servers that are in availability zone A, they will be served by the cache cluster that is in availability zone A. But the clusters have replication in between. So if they say, for example, the whole availability zone A goes down, the memcached objects and Redis objects will not be lost. Still, when the request comes back to M4, these M4 servers in availability zone B, it will still be served by availability zone B. So,
Okay. It's across the region. Okay.
it's across the region, but the servers that are in the same availability zone, they will always query their own cache cluster. They will not go to availability zone, like availability zone A server will never go to availability zone B elastic cache. They will always go to availability zone A elastic cache.
Okay. Makes sense. Good. Excellent.
All right, the second last design principle is optimize for cost. So how can we optimize for cost when I said in my first slide that cloud is almost the same cost as the on-premise data center? If you recall, I also said that the cloud needs to be rightly sized in order to bring cost optimization benefits. So you have to be very careful while designing whether you can use general purpose instances, whether you can use compute optimized instances, you can use memory optimized or storage optimized. It depends on the application and the type of the content that it needs to serve. Like say, for example, for a web server, I would not use a storage optimized instance or a compute optimized instance. I might use a general purpose instance or maybe a burstable instance, which is like a T2 or T1 instance. But say, for example, for a database, I would always use either a compute optimized or a memory optimized. Maybe if I'm using a NoSQL database that makes the indexing within the memory, I might use a memory optimized instance. If I'm hosting a service that actually requires a lot of I/O operations per second, I would use a storage optimized instance. So it has to be the right size of instance when you are designing a cloud. If you don't pay attention to what type of instance should go at what tier, then your cost would be skyrocketing in that case then. So as a general practice, the general purpose instances are used normally for application as well as for web server front ends, and compute optimized instances are used for the databases. But in some cases where the database requires more memory, you can use memory optimized also. Now, there is another type of instance called burstable performance instance. This burstable performance instance has certain level of CPU credits which it can use in order to do some CPU cycle bursts. So these are called T instances, or you can find is in T2 small, T2 nano, T2 large, T2 extra large. These instances have certain level of CPU credits with them, and if that credit expires, then they no longer serve the compute. So typically these type of instances can be used for test dev environments and non-production environments, but some of the companies also use them for the front-end web servers as well. The fixed performance instances are all the above ones that are mentioned there, general purpose, compute optimized, memory optimized, and the storage optimized instances. Now, there is each instance has a size starting from, I believe, micro now or nano now. So nano till 10x large, you can select any number of instances based on their compute capacity, their memory capacity, and their storage capacity as well. So what should be the approach? The question that I would pose to you is whether we should use many smaller instances or fewer large instances. I think we have explained this in the scalability part. What Amazon recommends is that we should use many small instances rather than having a fewer large set of instances, but it can depend on application to application. If the application requires a certain level of minimum sizing requirement, and that sizing requirement falls into a large instance, like say for example 4 core 16 GB is a large instance, then you have no choice but to host the application in a large instance. Typically, all the Windows instances, because of the compute and memory requirements of a Windows operating system, requires larger instances as compared to a Linux instance. Another rule of thumb: always rely on auto scaling in order to fit to the demand and pay for what you need. But having said that, not all applications are auto scaling compatible. If you try to fit auto scaling to an application that is not supporting auto scaling in a way that it requires a lot of configuration to be done when an instance comes up, then maybe you might end up doing more damage uh, than more benefit to the application. So auto scaling is not suitable for any of the applications that have large static architectures like SharePoint, like Microsoft applications, like any other single server-based applications. Auto scaling is best suited for applications that are very lightweight, smaller, distributed, and they are designed for parallel computing, like web applications, like API servers, like mobile applications or gaming servers, or anything related to HTML. The last point is always when you're designing, take the advantage of various different purchasing options that Amazon provides. You can always use RIs. RIs are called reserve instances, and you can save about 40% on the on-demand costs and make use of the cost benefits that Amazon provides for those instances that cannot use auto scaling. Now, for instances that can use auto scaling, always try to use either on-demand or spot instances. What is the difference between on-demand and spot instance? On-demand is an instance that actually available at a typical rate, and it's a disposable resource. You use it and you stop using it. You don't have to pay around it. Now, in contrast to on-demand instance, there is another type of instance called a spot instance. Spot instances are certain type of instances that Amazon makes them available due to the excessive capacity in the data center. They are going waste. So Amazon tries to sell those instances using a bidding strategy, and you can always make use of those instances. Like what I use them for is, say for example, a C4 extra large instance normally costs $200, and in a spot instance it costs $20. So why so cheap? Because it's actually going waste, and Amazon tries to make money out of it, and you can actually get that capacity for an hour or for 2 hours or for 3 hours at a very uh, discounted rate of 10% or 15% of the actual cost. Where it is usable, say you are running a NoSQL DynamoDB cluster, and this cluster makes use of 10 instances, for example. You can run 2 reserve instances, and rest of the instances you can run as spot instances. And you define a bidding strategy that whenever an instance is taken away by Amazon, you again bid for a higher cost, and you take the instances again for an hour or for 2 hours or for 3 hours. This process keeps on going when Amazon, like, you keep booking the instances and Amazon keeps taking away the instances, and at the end of the month, you would see that you just saved about 80% of your compute capacity by using spot instances. They are really helpful in deploying big data architectures like EMR, like Hadoop clusters, like ELK environment, because you don't need those instances all the time. While the load is not there, auto scaling takes care of that, and the compute capacity falls back to the reserve instances that you were running. And you can always define the maximum number of instances in your auto scaling environment. So this is what I use typically and mix on-demand and spot instances environment. So this is from the cost perspective. If you guys don't have any questions related to the cost, we can move to the last and the final point. All right. So last point, I think I don't have to spend much time on it because Ali has taken very well care of that. So from design principle perspective, security has to be built in. Always make sure that you use logically isolated VPC environments for your applications. Use bash channels. Ali has already taken a lot of point in explaining why a best host is required, why it needs to be there. Always make use of IAM, always use network ACLs and security groups, always use CloudTrail and CloudWatch environments. I have added two more points. One is Edge Firewall and Net Gateways, which I personally use in my cloud environments. This is not there in the paper, so I can mark this as red as well. But I thought of like, if we are defining security, then we should define some Edge Firewall part as well. The last point is from the use of web application firewall and SSL, which Lee already explained in the security white paper last time, that these webs can be deployed along with CloudFront, and you can do SSL across the board using the elastic load balancers as well. So this finishes up my 10th point. That brings me to another slide which tells you how many customers are using Amazon. So if we see the practical implementation of these design principles, we see a lot of companies making the use of Amazon. You would see CIA there, you would see NASA there, you would see media and content creation companies like Adobe there, you would see chatting companies like Slack there, online content provider like Netflix, Airbnb, pharmaceutical companies like Novartis, travel companies like Expedia. So Amazon guys must be doing something right? Otherwise, all of these bigger companies would not be making the use of Amazon. So I personally believe that Amazon has a lot to offer. It's only like within our reach. We just have to extend our hand and get all the benefits that it provides. So this finishes up my presentation. If you guys have any questions, I'm at all ears.
So these government agencies might be using Gov Cloud, or like we open our cloud.
So for CIA specifically, Amazon, when Amazon won the contract from IBM, actually IBM was the main contender. Amazon has created a separate cloud that is not connected to the internet for CIA directly.
Yeah.
All right. So one last thing. I am in love. Let's do one last thing. None of you asked how did I end up with these views.
I was about to ask, and I was looking for the icons. So yeah,
this is a beautiful tool. I'm going to show it to you now.
I have just downloaded the PPT from AWS, and the icons are.
You don't have to do that. So if people are awake, I'm going to show it to them. You can go to cloudcraft.co. You can log in. You can sign in with either email or Google, and you end up with this. Now, it doesn't end in there. You see the design component here. You see AWS components. You see common components. You see the auto scaling component and create availability zones.
Yeah, I thought it's Visio,
right.
and I saw the PPT file. It's
I
not
can put
Visio.
S3.
Oh, great.
I can connect this to my S3 bucket. I can do an elastic file system. I can do networking. I can do databases. I can do Redshift. I can do Elasticache. And the good thing is,
one is free software. I mean,
absolutely free, man.
And only for AWS.
Yep. Now, if you don't want to bring in your architecture from scratch, go to the library, deploy the blueprint architecture, and you get this, and you can modify this architecture to whatever you would like to do. All right. Very nice, right?
Wow, this is amazing.
Now I'll show you the best thing.
Zabardast, mate.
There is another thing called live. You can add your AWS account, and for the first time, if you guys are network architects, you would see a physical data flowing from your network diagram from here directly. And you can right click while live by adding your AWS account. You can right click and deploy this whole architecture in Amazon directly from this diagram.
So it creates the JSON file as well, right? So you can
No,
import it in
when
the.
you add your AWS account, it requires a paid subscription. What you can do is you can connect, and it does a live AWS sync with your environment. So you can define the architecture as well, and you can see that which instances are running, which data is flowing, which ELB is serving the request, and you can right click and you can see a number of requests going. You can see the CPU utilization of this box. You can see how many database requests this guy is serving. You can see how many files are being served by S3. You can see how many files are being cached by CloudFront. You can see with this load balancer how many requests are being received from the users. You can see on Route 53 how many DNS requests are being served. So this takes it to a completely next level of architecture.
So Farhan, this is two-way. Like you can import it into Amazon and you can also get from Amazon.
From Amazon as well, yes.
Oh boy, unbelievable.
All right, so this was my hidden gem. In the last, I kept it in the presentation to keep you guys awake.
This is really good stuff.
So it shows pricing as well.
Yes, so if I go to the pricing part, you would see here. So the basic subscription comes for free, but if you want to make use of this live part that I was telling you, you have to just shell out $49. So our company uses this as a corporate account, and it can you can deploy the architectures and see lots of stuff. So you can see
No,
cloudcraft.co
I
and
mean
check the
the
pricing.
have a calculator. We can use AWS calculator, right? But from here, I mean, can we see what
Yes.
the equipment instances pricing?
Yes, you can see the pricing, plus you can see the pricing per region. So if I click on this, Ireland, and the price gets changed, and then you can do a manual layout, or you can put in it can take the pricing directly from there as well. So you can change this from various different data centers to any to any available one. Like say for example, I want to check the pricing of an EC2. So, so from say for example text large, automatically the price get changed, and it tells you from here, it tells you what is the capacity of that instance as well. So some of the pricing will not be shown if the instance is not available in that region. So I will select an region that is mostly available. So see, if G2 instance is available in EU West, but it is not available in London, so the pricing will not be shown. So you see that it is 32 vCPU, 140 ECU, 60 memory, and this is the cost. So you can actually use this to build your whole cost architectures, and then you can export this to a shareable link or a downloadable image, or you can preview this also. The free version gets this grid only, but the paid version gets infinite grid. You can use it for any other purpose as well. Almost all of the functions of Amazon are here. But if it is not, it is not there in Amazon right now. All right. So what's new? If you open up, they keep on adding many things. If you check like new EC2 instances, DynamoDB. So this is how you will see when the live function is running, you would see like, it's active, it has this much GB, it has this many items, it has 3 write, 3 reads, 4 it is increasing directly. So it's quite nice. I mean, you can do so. If I play this, you would see like how they create it and then how the live environment is shown. So just try it out. All right, guys, this is it from my side.
नीचे
Any last questions you guys have? Or everybody checking Cloudcraft now?
yeah
Everyone
so
checking the
amazing.
same tab.
You so you have to create some special firewall rules or something to